Series circuits, our first foray into circuits. So you gotta start off, here's a thing pair share as pertains to appliances and electrical appliances. Mr. Heffley has a lamp, and a fan connected to an outlet in his bedroom. If Mr. Heffley turns his fan on, what do you think will happen to the light and why? Please take a moment to answer if need be, and then proceed to hit the play button on the video. On this video, Bear said. So 8.3 series circuits. So announcements, no media announcements. Just make sure you're keeping up to date with your work and turning in all missing assignments. What we're up to today is we're going to look at the basic components and introduction to circuits. So we're going to look at the simplest form of circuits today, get an idea of how circuits work, and then gradually we're going to layer on top of this to get more and more complex circuits, and eventually look at how electrical grids work, as in how all the way from the source of our electricity, aka say like solar panels, nuclear energy, or coal or gas or whatever, all the way up to how do we prevent electrical fires, how do we prevent breakdowns, and how do our electrical appliances in our houses work. Exploring circuits, how do circuits work, and how do components of a circuit affect one another, aka if we make a modification to a circuit, how does that modification affect another part of the circuit. Physics of batteries and resistors, and then we ask what causes resistance in a circuit. And what affects the current flowing in a circuit, okay? And how does this relate to everyday life? How do we see these applications and things we learn about in everyday life perspective? And how can we mathematically model circuits? Because one big thing is in order to design a circuit, you need a specific amount of current, you need a specific amount of voltage in a circuit. So those are all factors you have to consider when designing circuits, and hence you need to be able to mathematically predict what's going to be happening where in a circuit. So let's go through circuit components and symbols real quick. The following three components required for a circuit to work: the battery, resistors, and wire. So the battery we're already pretty familiar with, all right? So a battery is represented with this symbol right here. The longer line is the positive terminal, as shown here, and then the shorter line is the negative terminal of the battery. Resistors we're going to learn about down the line in this class. Resistors are, for the time being, can be thought of as anything that's an electrical appliance or hooks into a circuit, or hooks into electrical outlets. So like a light bulb is a simple example that we'll look at in this class. And a resistor is drawn by this ziggly line right here, this zigzaggy line right here. All right. And then lastly, wires. Well, we all know circuits have wires to connect things. We'll take a look at more specifically what's happening than just they connect things in this class. So here would be an example drawing of a circuit. So we have our batteries right here. We have a negative to positive, another negative to positive, another negative to positive. So we're going to have negative terminals right here, positive terminal right here, negative terminal, positive, negative, positive. And then we have three light bulbs or three resistors. So we're drawing those as zigzaggy lines right here. And that is the basic idea of a circuit, all right, or the basic sketching of a circuit. So series circuits are the first type of circuits we're going to learn about. In a series circuit, the resistors are added one right after the other, and hence we say that they're added in series. The same way that iPhones are released one after the other, we say that iPhones are released in series. You have the iPhone 8s series, iPhone 9s series, blah, 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 so on and so forth down the line. So the same thing applies with circuits. In a series circuit, the light bulbs are one right after the other. So we have a circuits exploration activity here. If you would like to do this, you can pause here and you can open up this link right here. It'll take you to a PhET activity, as you'll see here in a second. Rest said it'll open up the lab sheet, and then the PhET activity link is right here. But for this video, we're going to constrain ourselves strictly to the PowerPoint. So series circuits, all right, how do the main components work to make a circuit work? So the battery provides a source of voltage and thus sets up a potential difference. It causes an electric charge. As a result of this potential difference, this allows electric charge to flow from the negative terminal to positive terminal. Okay, remember that electrons want to move away from other electrons, so they're going to move from the negative terminal to positive terminal. Okay, and this makes sense if we think about it again in that electrons and negative electric charges move from low to high potential, and a negative terminal is a low potential, whereas a positive is a high potential. So the battery provides a source of voltage and thus sets up a potential difference. Okay, so it's kind of like the heartbeat or the heart of our circuit. Okay, the resistors slow down the current in our circuit. That's what you saw in the lab. If you pause to do the lab, If not, the resistors slow down the current of electrons inside the circuit. But more specifically, what this does is by slowing down the current of the electrons, energy is transferred from the electrons and converted into heat and light for our use. And this is what we see with light bulbs when current flows through light bulbs. Okay, so resistors are are devices designed to amplify electronic collisions with atoms. So electrons collide with atoms inside resistors much more than they do in any other part of the circuit, and hence as a result of these collisions, they take the kinetic energy from the electrons and transform that energy into heat and light, or whatever energy source or whatever type of energy we may need for a device that we're trying to power. Okay, hence is why we call them resistors, because they resist electric current and act to slow down the electrons by transforming the kinetic energy electrons into heat energy. Now, what's really happening inside resistors is a little bit more complicated and goes into material science and condensed matter theory, but that's something we're not even going to try to touch in this class. So when energy is lost inside of a resistor, we call that a voltage drop, a loss in electrical energy. Now, I'm being a little bit liberal with my terms here, so my physicist buddies and I here would kind of say that's not 100% the whole story, but for our intents and purposes, this accurately does describe what is happening inside a resistor. Okay, so voltage drop is a loss in electrical energy that happens when our electrons move through the resistors. Okay, and lastly, the wires provide a conductive pathway for electrons to travel. Again, our electrons want to move from the negative terminal to positive terminal, so there needs to be a full, complete connection from negative to positive. We can't have one end unclipped and the other end clipped in. Both ends have to be clipped in. The circuit has to be closed, okay? In addition, the circuit also has a conductive pathway. If the pathway is conductive or is not conductive, electrons will not flow as well as if they're going through a conductive material, and as a result, your circuit will not be very effective, to the point that essentially it's like electrons are not really flowing through your circuit at all. So how do resistors work? All right, what are resistors? So everything that electricity flows through, that electric current flows through, has resistance as a result of there being atoms and molecules that makes up those objects, whatever the electric current is flowing through. So resistance is measured in a unit of measurement called ohms, and it's caused by electrons colliding with atoms inside of a wire. Okay, so in this way, it's kind of like friction, the same way that you rub your hands together. There's collisions between the surfaces of both your hands. Okay, so the resistance of wire / resistors depends on the following factors: the cross-sectional area / width of the wire. Okay, so how wide our wire is. To give you an idea, if we think of our wire as a PVC pipe that transports water, the wider our pipe is, the more water is going to be able to flow through, and hence there's going to be a larger current of water. Whereas the narrower our pipe is, the less water is going to be able to flow through, and thus less current will be able to flow through. So as a result, the wider the wire, the more space there is for electrons to move across, and hence there's less resistance. Okay, so there's an inverse relationship between width of the wire and resistance. Okay, the second thing is the length of the wire. The longer the electrons have to travel, the more collisions will occur. There's going to be, and hence there's going to be more resistance. If you imagine this as kind of like the Han Solo asteroid run or whatever it's called in Star Wars, because I'll admit not too big fan of Star Wars. It's kind of similar to that in that the longer you travel through an asteroid field, the more probable it is that you're going to eventually run into an asteroid. Same thing happens here, is that the longer your electric current travels through a wire, the longer your wire is, the more probable that collisions are going to occur, and hence there's going to be more resistance. So there's a direct relationship between length of the wire and resistance. Conductivity of the wire we've already talked about. So the more conductive the wire is, the more easily charge will flow across it, and hence there's going to be less resistance. So the more conductive the wire is, the less resistance it will produce, and vice versa. So there's an inverse relationship between conductivity and resistance. Then lastly, this one is a bit unlikely at first, but it does actually make sense when we think about it, in that temperature is also a factor that affects resistance, because the higher temperature of the wire, the more electrons and atoms are going to move randomly, which is going to result in increasing collisions, and it's going to increase chaos. And as a result, this will increase resistance. So there's a direct relationship between temperature and resistance. In fact, you can actually feel this a little bit when a circuit heats up. When a circuit heats up. In fact, this is actually how electric thermometers actually work a bit. Now, we have to be subjected to Disney. Anyway, so here is a useful video. I'll put it on mute here. So here's a useful video that showcases the relationship between temperature and resistance. So what we have here is a circuit that is fully complete. All right, so we go from our negative terminal through this exposed filament, and then the exposed filament runs into this light bulb, and this light bulb goes back into the positive terminal. And so as a result, there is electricity flowing, there is an electric current flowing through the circuit, but it's not enough to light this bulb up right here. What happens is when our guy blows on the filament, he is reducing the temperature around the filament, and hence that's also going to reduce the temperature of the filament as a consequence. And as a result, the temperature of the filament dropping, the resistance inside the filament drops, which means there's more current able to flow through circuit, resulting in the light bulb lighting up, as we see right here. Now, the same thing happens again is if he takes a ice cube and puts this in active filament, that's going to result in a drastic decrease in temperature inside of the filament, and as a result, it's going to result in a drastic decrease in resistance inside of the filament. And as a result, the current is going to skyrocket inside of our circuit, resulting in this extremely bright output of light and thermal energy. So that is an example of all the factors at play for how resistors work. A little bit more on the microscopic scale when we're considering collisions between atoms and electrons. And it's these collisions that results in heat being produced as the kinetic energy of the electron is transformed into thermal energy during the collision. So next we come to Ohm's law. Ohm's law relates current, voltage, and resistance. So as you all noticed in your labs, the amount of current flowing in a circuit is dependent on two factors. The voltage of the battery. We see there exists a direct relationship between the voltage of the battery and the current. I forgot to put current in here. I'll go back and do that. And that makes sense if we go back thinking to our waterfall analogy. If our waterfall is like voltage, then that means the higher up our waterfall is, the greater the difference in height. It means there's a greater voltage, and that means water is going to hit the bottom of the waterfall at a faster speed. And the same thing happens in a circuit is that the greater the voltage is, the greater potential there is for electrons to move, and hence there's going to be greater current in your circuit. And the second factor we see is the resistance of a circuit. We see there exists an inverse relationship between the resistance of the circuit and the current in the battery. Namely that if we increase resistance, there's going to be more collisions between electrons and atoms, and that's going to result in a decrease in current. In a way, this is analogous to Newton's second law, in that the acceleration of an object depends on force and mass. If we recall, that object accelerates depending on how much force is acting on it, and depending on how much mass that object has, because that mass acts as inertia, as a resistance to a change in motion. The same thing happens with an electric circuit, in that the current of an object depends on the voltage. In fact, in classical physics, voltage is also known as the electromotive force, even though it's not technically a force, okay? And that current also depends on the resistance inherent in the circuit. Now, the only difference here that I have an issue with here is current is more like velocity than it is acceleration. So it's not a 100% exact accurate analogy, but it suffices for connecting it to prior concepts. And just as there is an equation to describe Newton's law, there's an equation to describe this relationship between voltage, resistance, and current. It's known as Ohm's law, and states that the electric current is equal to the voltage divided by resistance, or perhaps written in a more mathematically convenient form, voltage across a resistor equals the current in that resistor, through that resistor, times the resistance of that resistor, okay? And this is analogous again to F equals ma. Voltage would be our force F, m is going to be our mass, and then, current is going to be our resistance, current is going to be my acceleration a, and then resistance is going to be my mass m, okay? So this equation encapsulates the relationship between voltage and resistance. In fact, we can see an inverse relationship between resistance and current, and a direct relationship between current and voltage. So, analogies to gravity and rivers. Again, tying this back to something that's a little bit more tangible for us, okay? The voltage/potential difference is like a difference in height in a water source. If we want water to fall or flow, we need a difference in height, just as a potential difference, aka voltage, is needed to propel electrons. Wires and resistance. The width of the river will limit how much water is able to flow in the river, the same way that the width of a circuit or the width of a wire will motivate how many electrons can flow through the wire at any given moment, aka the current. The rocks in the river act like atoms inside of a resistor, interrupting the flow of the current in the river. So the more rocks we have in our river, the higher resistance we have, and the less flow of water we're going to have. And then lastly, if we have an open circuit where current can't flow, it's like where electric current can't flow. It's like we have a dam in the river where a wire is broken, no current can flow. The same way that if we dam a river, no water is able to flow inside of the river. All right, so we can pause here to think, pair, share. Please take a moment to answer, and then when we're ready to roll, hit the play button on this video here. Okay. So by switching on my fan, okay, we ask, why is it that the light bulb momentarily dims for a moment when I turn my fan? So the reason being is that by switching on my fan, I'm adding new resistor, okay, a fan in this case instead of a light bulb, that causes the current in these circuits in my bedroom walls to momentarily decrease. That is if this is a series circuit. If it's a parallel circuit, it actually has a slightly different effect. Parallel circuits adding resistors in a parallel circuit, as we'll learn, will actually act to decrease resistance. So this causes the light to dim until the circuit is able to compensate and meet the new power demands in the bedroom. Okay. So as a result of adding resistance, current momentarily decreases throughout the whole entire circuitry of my bedroom walls until the circuitry compensates. Okay. You might see this if you turn on a vacuum cleaner, or if you draw too much power from a electrical outlet. Okay. If you add too much of a electrical load to electrical outlet. Now, if it's a parallel circuit, the reasoning is a little bit different, and we'll take a look at that down the line. And if I'm going to be honest, since I'm not an electrical engineer, I am quite ignorant if a electrical circuit such as electrical outlet is a series or parallel. I would imagine it's actually probably a parallel, but it could be a series. So there's something I can learn too as well. So if we want to analyze circuits, say know how much current flows through a circuit at a given point, or know what the voltage drop is across a certain resistor, okay, we need to be able to calculate mathematically the relationship between voltage, resistance, and current in any given part of our circuit. So we make use of what are called Ver charts in order to analyze this. So Ohm's law can be used in conjunction with one piece of information about a component organized in a chart to determine current, resistance, and voltage drops in any single one component. Okay, so the following rules are necessary for series circuits in order to carry out a Ver chart. Okay, they are absolutely necessary. You get these rules down, it's like a game. The Ver charts become very, very easy to do. Otherwise, the Ver charts are going to be hell on earth. Okay, so in a series circuit, the following rules are very useful. The total resistance of a series circuit is the sum of all individual resistors. So to give you an example, if R1 is 10 ohms, R2 is 20 ohms, and then R3 is 30 ohms, the overall resistance of the circuit is going to be 10 plus 20 plus 30 ohms, or 60 ohms. Kirchhoff's loop rule states that the sum of the voltage drops in each resistor is equal to the total voltage of the battery, okay? The idea being is that the battery is providing 12 volts, okay, of energy, electrical energy per charge for our circuit to work. So we have 12 volts available to power any electrical devices that are hooked into our circuit, aka whatever resistors we put in a circuit. So as a result, the resistors are going to use all of that electrical energy to power electrical devices. So that 12 volts of energy needs to be used around the circuit. So each resistor is going to use some amount of the 12 volts. And if you so as a result, if you sum together the voltage drops across each resistor, you're going to get 12 volts lost. AKA energy in, the energy provided to the circuit by the battery must be used by circuit, so it's going to be equal to energy out. So if we look right here, 2 volts of energy, electrical energy used right here through this resistor is plus 4 volts plus 6 volts gives you 12 volts. 2 plus 4 plus 6 is 12. So we see that energy out is equal to energy in. Conservation of energy applies. And then we also see that the current throughout the circuit is the same. All right, so if 0.2 amperes is the current throughout our circuit, that's going to be the same current going through R1 as through R2 as through R3. Why? The reason goes back to charge conservation. Again, if we think about this like a river or like water flowing through a pipe system, there's no water lost through a pipe system at a point. The current of water is the same throughout all points because the water is conserved. There's no leaks or anything like that if it's an ideal pipe system. Same way, there's no electrical charge lost to the outside world inside of a circuit. And there's no electrical charge created from nothing. You can't create electrical charges from a snap like that. So as a result, there's charge conservation. So as a result, the current throughout the circuit must be the same through all components, okay? So these are our rules for series circuits right here. Okay, now for parallel circuits down the line, we'll see the rules are slightly different. So you need to make sure you have these rules 100% down for series circuits, okay? So let's look at our first example of a Burr chart. Why do we call it a Burr chart? The reason being is we use Ohm's law, V equals IR, or Burr for short, in conjunction with a chart that breaks down each circuit into its individual components to analyze the voltage drop and current through each component of our circuit, okay? So what we're going to do is we're going to first fill in immediately what we know here, okay? So from our diagram here, we immediately know that the resistance of R1 is 100 ohms, resistance of R2 is 300, and R3 is 50, and that the voltage provided by the battery is 9 volts. So on our table here, in our rows, we're going to have the individual resistors, and then we're going to have the total overall circuit, okay? And then in the columns, we're going to have the voltages, okay? Currents and resistances of each component, okay? Hence the Burr acronym, okay? So the resistance of R1 is 100 ohms, the resistance of R2 is 300 ohms, and resistance of R3 is 50 ohms. All right, so as a result, the total resistance is 450 ohms. Nope, I suppose not. So as a result, our total resistance of the circuit is going to be sum of each individual resistance. So that's going to be 450 ohms for our total resistance. So now we have 9 volts and we have 450 ohms for our total voltage, our total resistance. So now what we can take note of, okay, is if we know 2 entries of any single row, we can use Ohm's law to determine the third entry. Say, for example, the current in this case, okay? So in this case, we know V and R, so that tells us we're going to need to divide both sides by R to get I by itself. So our current is going to be equal to our voltage divided by resistance. So in this case, our total current is going to be equal to 9 volts divided by 450 ohms, or 0.02 amperes. So now what do we do from here? We still have 6 entries that we need to fill in, and we can't use Ohm's law since we don't know, since we have 2 unknowns for each row. What we can make use of for a series circuit is, again, charge conservation dictates that the current throughout is the same, so we can fill in 0.02 amperes for the current through each individual resistor. So now we can apply Ohm's law to each individual row to figure out the voltage drop across each individual row. We can do voltage equals current times resistance, V equals IR, to figure out our voltage drop across each individual resistor, which gives us 0.02 times 100, or 2 volts for the voltage drop across R1, okay? We can do 0.02 times 300, or 6 volts of voltage drop across R2, and 0.02 times 50 for 1 voltage drop across R3. So what that tells us right here is this tells us how much energy is being dissipated per electron across each individual resistor. 2 volts across R1, 6 volts across R2, and 3 volts across, or 1 volt across R3. And we see this makes sense because there's less resistance in R3 compared to R1. As a result, less energy should be dissipated in R3 compared to R1. Now, we've worked with a lot of numbers here. We've worked with specifically 12 numbers, so we need a quick way to make sure our work is correct without having to go back and check and everything. So what we can do to check to make sure our work is correct is apply Kirchhoff's rule, and we can check and see that the sum of the voltages for each component is equal to the total voltage of the circuit, aka the total voltage drop across each resistor is equal to the total voltage provided to the circuit by the battery. So here we get 2 volts plus 6 volts plus 1 volt gives us 9 volts, matches up with the total voltage of our battery. So here's an example of our Burr charts. Now let's go through a second example of Burr charts. Okay, because they are quite tricky, it is good to check and make sure that we have as much practice as is need be for this, okay? So if you are comfortable with Burr charts, you can skip right to classwork. If not, you can check out this additional example and then also do a check for understanding on the next slide. So for a circuit shown at right consisting of a 120 volt battery and 3 resistors in series, determine the current in the circuit and the voltage drop across each resistor, okay? So same scenario as before. I'm never going to throw any curveballs, okay? Because the main idea here is we'll always typically know what the voltage source is, aka we can read a D-cell battery has 9 volts or 6 volts or whatever it is, And most of the time we know what the resistances in the resistors are because we can design the resistors for the resistance that we want. The thing that we're interested in calculating that we can't always directly measure, at least without the help of a voltmeter, is the current and voltage drop across each component of our circuit. And so that we do need to be able to calculate, okay? So we start again by filling in what we immediately know, okay? We know that the voltage provided by the battery is 120 volts, and we know that the resistances of our resistors are 15 ohms, 5 ohms, and 20 ohms. So using this, we can find out the sum of our total, we can find the total resistance by taking the sum of each resistor, and that gives us 40 ohms. Now our voltage is 120 volts for a whole entire battery, so our total voltage is 120 volts. All right, so next we can apply Ohm's law in this row right here to determine the current in our entire circuit. So we take 120 volts, our V, and we divide it by resistance R, 40 ohms, and that gives us that our overall current is going to be 3 amperes. Next, again, we can apply charge conservation. That tells us, that dictates that the current throughout is going to be 3 amperes. And then lastly, in order to find the voltage across each individual resistor, we take the current for each row and multiply that by the resistance for each row. So our voltage here is going to be 3 times 15 or 45 volts. Our voltage here in our second row is going to be 3 times 5 or 15 volts. And our voltage for the last row is going to be 3 times 20 volts or 20 ohm, 3 times 20 or 60 volts. Okay? So if we check here, we can again check and see that 45 plus 15 plus 60 gives us 120. So we can see that Kirchhoff's rule is satisfied, that conservation of energy is satisfied in this specific case. All right? Now, as our last check for understanding here, for a circuit shown at right consisting of a 10-volt battery and 3 resistors in series, determine the current in the circuit and the voltage drop across each resistor, okay? So you have a 10-volt battery, you have 20 ohms right here, 19 ohms in R23, and then 20 ohms in R4. Do not be tripped up by the fact that this is called R23. You can call the resistors whatever name you want, so long as the math is tidy and organized, okay? So pause the video here, and then when you're ready to go, please resume. All right, so we pick things back up. Again, our keys are to fill in immediately what we know, determine the total resistance of a circuit, use Ohm's law to determine the current in the entire circuit, and then apply charge conservation to the current column. Lastly, we apply Ohm's law to find the voltage drop for each resistor, making use of Ohm's law equation V equals IR. So here we know that the total voltage across the battery is 10 volts. We know that R1 is going to be 20 volts or 20 ohms, so that's our resistance right there. We know R23 is going to be 19 ohms, so that goes in our resistance column for R23 row. And then we go across, and then R4 is equal to 20 ohms, so that's resistance right there, okay? Overall, our overall resistance is 20 ohms plus 19 ohms plus 20 ohms, or 59 ohms. So 10 volts is our total voltage, and our total resistance is 59 ohms. So we can find the current in this overall circuit, the overall current in our entire circuit, by applying Ohm's law. We take our 10 volts and divide by 59 ohms. And that gives us a little bit over whatever 1/6 is. 10 divided by 59 is a little bit more than 1/6, which is 0.17 amperes. And then, oh no, where do I go from here? Again, remember we apply charge conservation. Charge is conserved, so that means the current throughout the entire circuit is the same. So 0.17 amperes is going to be our current throughout. And then lastly, we can find our voltage across each resistor by taking 0.17 amperes and multiplying it by 20 ohms, okay? So 3.4 volts is going to be the voltage, or excuse me, for the first row, 0.17 times 20 ohms gives us 3.4 volts for R1. 0.17 times 19 ohms gives us our voltage drop across R23, 3.2 volts. And then R4 has the same voltage drop as R1 because it has the same resistance and same current as R1. And then lastly, we can add up these three voltages to see again that we get 10 volts outputted of our circuit equal to 10 volts inputted by the battery. So you may be wondering at this point, why is all of this so useful, especially, especially since it seems like we're just number crunching at this point. What's the point of these charts? So the point of these charts is that this really is the foundational starting point, the cornerstone for designing circuits. if you look at any component, if you look at any electrical appliance, they often have an input voltage and an input current, and that tells you the maximum amount of current that can be passing through that component, and also tells you the voltage required in order for that circuit to, or for the electrical component to work. So if these electrical components hook into a circuit like the resistors do, then we need to be able to calculate, if we hook these electrical appliances into our circuit, what is the current output going to be in the circuit? Will that be enough to power our devices? Will it be too much to power our devices? AKA, are we going to have like what we saw temporarily with the fan turning on and the lamp turning on? Will we be drawing too much electrical current, and as a result, maybe be at risk for electrical fires or blowing a fuse? And so as a result, we need to know specific numbers, and that requires us to know specifically what's happening inside of our circuit. And this helps us to design different circuits to accommodate different designs and different electrical appliances. And so as a result, the verb charts are a useful way and very efficient way of figuring out this information. Otherwise, you would have to apply a bunch of linear algebra and a bunch of equations, and oh man, it gets messy real quick. So the next step from here, if you're an electrical engineer, would be to apply verb charts to more complex circuits. And then if you're an electrical engineer, you would learn to design code, write computer code that could calculate verb charts for you. Because it is true that yes, we can run computer code and run computer programs to calculate these numbers for us, but at the end of the day, that still requires somebody who understands verb charts and the physics behind these circuits in order to design the computer code. The same way that the computer code that dictates how a video game runs needs to be designed by a person who understands physics to implement physics in that computer code. So that gives you a little bit idea of how these verb charts are useful more than just crunching numbers, all right? So even though it may seem like busy work right now, hopefully I've given you a glimpse through this video of how they are useful, even if it may not seem immediately useful through this video. And this is our lesson on series circuits.